I will discuss about principle of hydraulic machines and system design. Here I briefly lecture wise schedule of the course content. First lecture I will discuss about introduction to hydraulic machines, classifications and operational principles, and there are other lectures where I will discuss different parts of this course. The first lecture I will talk about hydraulic machines, classifications and operational principle. So, before I discuss about hydraulic machines, first I will discuss about the classifications of fluid machines. So, hydraulic machine is which falls under the fluid machines when working fluid is essentially water. So, let me first discuss about the classification of fluid machines. There are different issues by which I can classify fluid machines. First one is essentially based on the principle of operation. First one is essentially based on the principle of operation. Based on the principle of operation, we can classify fluid machines into two different categories. First one is positive displacement machine. Positive displacement machines, and second is turbo machines. So, based on the principle of operation, we can classify fluid machines into two categories. One is positive displacement machine, other is turbo machines. So, what is positive displacement machine? What is positive displacement machines? The machine whose functioning, I am writing the machine whose functioning depends essentially on the change of volume of certain amount of fluid, within the machine, are the machines whose functioning depends essentially on the change of volume of certain amount of fluid within the machine are known as positive displacement machines. So, the machines whose functioning depends upon the change of volume of certain amount of fluid within the machine, those machines are known as positive displacement machine. The word positive displacement comes from the fact that there is a physical displacement, there is a physical displacement of boundary of certain fluid mass as a closed system. So, the word positive displacement comes from the fact that there is a physical displacement of the boundary of certain amount of fluid mass as a closed system. Okay. The next is turbo machines. The next is turbo machines, right. So, turbo machines are the machines whose functioning depends basically on the principle of fluid dynamics, So, turbo machines are not the positive displacement machine. Turbo machines are machine whose functioning depends basically on the principle of fluid dynamics, right. Turbo machines are very often, rather often referred to autodynamic device because they are specifically designed to transfer energy to or from a so-called working fluid through the action of force generated fluid dynamically by a or from a rotor. So, I am telling turbo machines are machines whose functioning depends basically on the principle of fluid dynamics. Turbo machines are often referred to autodynamic machine because they are specifically designed to transfer energy to or from a so called working fluid through the action of force generated fluid dynamically by a or from a rotor. Okay. This is so whatever we have discussed, that fluid machines can be classified based on the principle of operation, that is what we have discussed till now. Now, these turbo machines are called pump when they absorb power. So, turbo machines are called pump when they absorb power, and they are called turbine. So, pump is a turbo machines when, because pump is a kind of turbo machines which absorb power from the working fluid through the action of force generated fluid dynamically, and turbo machines are called turbine or sometimes known as prime mover when they produces power. So, when turbo machines absorb power, they are a class of turbo machines. I mean, they are known as pump. Turbo machines are called turbine or prime mover when they produces power. right. So, from this we can say that pumps work done on the fluid, whereas in turbine the fluid does work, on the machine. So, we are calling turbo machines are pumps when they absorb power, and they are called turbine when they produces power. From this we can say that in pumps work done on the fluid, whereas in case of a turbine fluid does work on the machines. Now, there are, whenever you are calling it pump or turbine, there are two important rotating elements we will discuss by today in a later time. So, next is we can classify fluid machines again, classification. So, till now we have discussed about the classification of fluid machines in general. As I said that hydraulic machines are a class of fluid machines when working fluid is water. Now, this fluid machine can be classified based on the direction of fluid path in the rotating element, based on the direction of fluid path in the rotating element. Before I elaborate this aspect, let us discuss about rotating elements. In case of a pump, this rotating element, the rotating element for a pump which is known as impeller, Essentially, impeller is hub plus blades. So, the rotating element for the pump is the impeller, which is essentially hub plus blades. Similarly, the rotating element for the turbine, rotating element is known as runner, and again this is hub plus blades. So, hub plus blades is known as runner for a turbine, and the same thing hub plus blades which is known as impeller for the pump. So, now when you are going to discuss about the classification based on the direction of fluid path in the rotating element, we can again classify into two categories. First one is the path of the fluid, through the rotor, or rotating element, whatever telling, through the rotating element or rotor, may be mainly in the axial direction, So, path of the fluid through the rotating element or through the rotor may be mainly in the axial direction, that is along the axis of the shaft, along the axis of the shaft of the machine. So, if the path of the fluid through the rotor or rotating element is mainly in the direction, in the axial direction, that is along the axis of the shaft of the machine, then these are known as axial flow machines. It may be a pump, it may be a turbine. So, this is known as axial flow machine. So, axial flow machines, that means when path of the fluid element is mainly in the axial direction, that is in the direction parallel to the axis of the shaft of the machine. These axial flow machines, or there may be a case when path of the fluid through the rotor. So, when fluid is within the rotating element or rotor, then if the path of the fluid is rather through the rotor is in the radial direction, that is in the direction perpendicular to the axis of the shaft, perpendicular to the axis of the shaft of the machine, then these machines are known as radial flow machines. We call radial flow pumps, or the turbine may be radial flow. So, when path of the fluid element or path of the fluid through the rotating element is mainly in the radial direction, that is in the direction which is perpendicular to the shaft of the machines, then these are known as radial flow machines. Or there may be a case, the last one, there may be a case when path of the fluid element or path of the fluid is path of the fluid through the rotor is in both the direction. When path of the fluid through the rotor is in both the directions, that is combination of radial and axial direction. So, when path of the fluid in the rotating element is in both the direction, that means combination of both the axial and radial direction, then these machines are known as mixed flow machines. Then the machines are known as mixed flow machines, right, either mixed flow pump. So, we have discussed about the classifications based on the direction of fluid in the rotating element. The rotating element is known as impeller in case of a pumps, which is essentially the hub plus blades. This rotating element is known as runner in case of a turbine. This is again hub plus blades. Finally, we can classify fluid machines based on the direction of energy conversions. So, last we will discuss about classification based on the direction of energy conversions. This is very important. Classifications based on the direction of energy conversion, right. So, this is the last classifications. So, first we have discussed about the classification based on the principle of operation. There we have seen that there is a positive displacement machines and turbo machines, Turbo machines are called pump when they absorb power, and they are called turbine when they produces power. Then we have discussed about the classification based on the direction of fluid in the rotating element. There may be direction of fluid in the axial direction, that is in the direction parallel to the axis of the shaft of the machine in case of a axial flow machines, or the direction of fluid in the rotating element may be in the radial direction, that is in the direction perpendicular to the shaft of the axis of the machine, then perpendicular to the axis of the machines, this is known as the radial flow machines, or there might be a case when fluid path in the rotating element is in the both directions, that is the combination of radial and axial direction, and that is known as axial flow machines. Finally, we will discuss about the classification based on the direction of energy conversions. So, the classification based on the direction of energy conversion. So, we can classify again. So, the device in which, or machine we can say, in which kinetic potential or intermolecular energy held by the fluid is converted in the form of mechanical energy, in the form of mechanical energy, of a rotating member is known as turbine. So, we can classify based on the direction of energy conversion. The first one, the device in which kinetic potential or intermolecular energy held by the fluid is converted in the form of mechanical energy in a rotating member is known as turbine, right. The machine on the other hand, where mechanical energy from moving parts is transferred to a fluid to increase its stored energy, by increasing either its pressure or velocity, and also an overall rise in specific enthalpy, and also an overall rise in specific enthalpy. Are the machines on the other hand where mechanical energy from moving parts is transferred to a fluid to increase its stored energy by increasing either pressure or velocity, and also an overall rise in enthalpy, are known as pumps, compressors, fans or blowers. So, the last classification, that is based on the direction of energy conversion. First of all, the device in which kinetic, potential or intermolecular energy held by the fluid is converted in the form of mechanical energy of a rotating member is known as turbine. On the other hand, the machines where mechanical energy from moving parts is transferred to a fluid to increase its stored energy by increasing either its pressure or velocity and also an overall rise in enthalpy are known as pumps, compressor, fans and blowers. So, this is all about the classification of the fluid machines. Since in this course I will focus on the hydraulic machines. So, now I will go to the classification of hydraulic machines. So far we have discussed that there might be hydraulic machines again is a class of fluid machines where working fluid is water. So, we can hydraulic machine we can divide into again two categories. So, hydraulic machines one is, as I said, that there be again positive displacement pump, it may be a positive displacement pump or I can say that there may be pumps, hydraulic machines pumps, or we have a turbine, hydraulic turbines. So, hydraulic machines we are dividing into two parts, two categories, one is pump, another is turbine, because we have seen that in case of a pumps, it is hydraulic machine is a class of fluid machines where working fluid is water. In case of a pump, it absorbs energy, but hydraulic turbine it produces energy. So, pump again we can classify into two different categories. One is rotodynamic pump, and other one is positive displacement pump. So, as I said that positive displacement pump, there is a physical displacement of the boundary of certain fluid mass as a closed system. So, positive displacement pumps and rotodynamic pumps. Rotodynamic pumps again further classified that I have discussed that based on the direction of fluid path, it may be a radial flow, pump, it may be a axial flow pump, and it may be a mixed flow pump. So, and turbine again it may be a radial flow hydraulic turbine, it may be a axial flow hydraulic turbine. So, this is the broad classification of hydraulic machines, pumps and hydraulic pumps and hydraulic turbines. Pumps can be classified into two categories, positive displacement pump. There are so many positive displacement pump, screw pump, then we have gear pumps, vane pump, we have reciprocating pump, all reciprocating pump, or we have gear pump. All these are positive displacement type, while we have a rotodynamic pump. Again, rotodynamic pump can be subclassified into three categories: radial flow machines, radial flow pump, axial flow pump and mixed flow pump. Okay. So, now we will discuss different pumps one by one. So, first we will discuss about the rotodynamic pump. Rotodynamic pump, as I said that this rotodynamic pump can be sub-classified into 3 categories. One is radial flow, another is axial flow, and last one is mixed flow type. So, rotodynamic pump can be subclassified into 3 categories: radial flow pump, axial flow pump and mixed flow pump. As I have discussed that in case of a radial flow pump, the direction of fluid in the rotating element is in the mainly in the radial direction, that is in the direction perpendicular to the axis of the machine. In case of axial flow machines, the direction of the fluid in the rotating element is only in the axial direction, that is in the direction parallel to the axis of the shaft of the machine, and in the mixed flow machine the fluid direction may be in both parallel and both axial and radial. So, in case of a radial flow machine, sometimes we call the radial flow pump. So, radial flow pump sometimes is known as centrifugal pump, is a commercial name, centrifugal pump. We in most of the undergraduate textbook it is written centrifugal pump. Centrifugal pump is the commercial name of the radial flow pump, because in a radial flow pump, by virtue of centrifugal action, we develop head of the water. So, but it is radial flow machines, because the direction of fluid in the rotating element is only in the radial direction, axial flow machine and mixed flow machines. So, in case of if I draw centrifugal pump, so we will discuss first about the radial flow pump, or it is known as centrifugal pump also. Centrifugal pump, I should suggest to call it a radial flow machines, because if only because of the presence of centrifugal action, if we call it centrifugal pump, in a mixed flow pump there is again centrifugal action is present. So, again we have to call it centrifugal pump. So, it is always better to call it radial flow machines or radial flow pump. So, if I draw a schematic of a radial flow pump, so we are drawing a pump impeller. So, small, this is known as hub, and there are many blades. So, these are blades. This hub plus blade, as I said, this hub plus blades, this is known as impeller, which is rotating element of pumps. It may be a radial flow, axial flow or mixed flow. So, this is radial flow, and the direction of fluid element, this is the direction of axis is perpendicular to this board, and fluid is going outwards. So, which is in the perpendicular to the direction of the axis of the shaft. So, this is radial flow machines. If I take a cross section view, it looks like this. So, if I draw, then fluid moves in this direction. This is the axis of the shaft of the machines, while the fluid is in the perpendicular direction. So, this is radial flow machines, and this radial flow pumps, I mean, is very often used in domestic purposes. The applications are in domestic purposes for lifting water in multi-storied building, or sometimes it is used in aircraft engine, and aircraft engine it is also used. Domestic purposes, mainly used for domestic purposes or sometimes used in aircraft engine. So, special feature of this pump is when flow of fluid in the rotating element is perpendicular to the axis of the pump, then pump is called radial flow pump. So, we should remember when flow of fluid in the rotating element is perpendicular to the axis of the pump, then the pump is called radial flow pump. It is used mainly in the domestic purposes or sometimes it is also used in aircraft engine. It is used where, very important, where relatively low discharge, and it is used when relatively low discharge and high head, rather moderate to high head is required. So, it is used in places where we require relatively low discharge and moderate to high head, then we generally go for installation of radial flow pump. The radial flow pump, when flow of the fluid in the rotating element is in the perpendicular direction of the axis of the pump, then we call it radial flow pump. This is used in places where we require low head and moderate to high discharge, that is low Q and moderate to high discharge and moderate to high H. So, when we require low discharge, low Q flow rate and moderate to high head, then we go for installation of radial flow pump. It is used mainly in the domestic purposes, sometimes it is used in the aircraft engine. Next, we will go for the axial flow pump. So, again I will draw a schematic. So, this is hub plus blades, which is known as impeller. So, these are pump casings. This is casing which surrounds the impeller. This is known as blade, and this is hub. So, hub plus blades, which is impeller, which is surrounded by a casing. Now, we have three directions Z, R and theta. So, R theta directions, pump is rotating in these directions, right. So, when flow of the pump, special feature of the axial flow pump, as I told you already, that I have already discussed about the direction or classification of fluid machine based on the direction of fluid. So, we can call it pump when it absorbs power. Similarly, for the axial flow pump, we can call it axial flow pump when flow of the pump, when flow of the fluid or flow of fluid in the rotating element is in the axial direction of the machines or pump of the pump. What is axial direction? That is in the direction parallel to the axis of the machines or pump. Then when flow of fluid in the rotating element is in the axial direction of the pump, then the pump is called as axial flow pump, right. So, here mainly flow of the pump, the flow of the fluid in the rotating element is in the axial direction of the machines or pump, and it is axial flow pump. Axial flow pumps is used, very important. Axial flow pumps are used in places where you require load head but high discharge. Used in places where low head and high discharge or high flow rate is required. So, axial flow pumps are used in places where we require low head, but we require very high discharge. There are several places, mostly in mines, irrigation purposes, and coal mines. So, the application of axial flow pumps are in the coal mines or and in the irrigation purposes, because in that cases we require high discharge, but head is low. We require low head. We do not require very high head. So, these axial flow pump find applications in those areas. Last, we will discuss about the mixed flow pump. Mixed flow pump So, this is again pump axis, this is blade, this is hub, this is pump casings. Now, here the blade or the hub makes an angle alpha with the axis of the machine. So, this is angle alpha. So, there are two directions of, one is axial direction, another is radial direction. So, here alpha for the mixed flow pump is typically from 15 to 30 degree. When alpha is 15 to 30 degree, it is mixed flow pump. It is mixed flow pump, and flow of fluid in the pump is in both the axial as well as radial direction. So, in case of mixed flow pump, as we have discussed, the flow of the fluid in the rotating element is in both the direction, that is both in the axial as well as radial direction. Here I have drawn a schematic where alpha is the angle made by the blade with the axis of the machines, with the axis of the palm. Alpha typically varies from 15 to 30 degree for when it is 15 to 30 degree, typically varies from 15 to 30 degree for mixed flow palm. Note that if alpha becomes 0, that is, it is purely axial flow machines. So, when alpha is equal to 0, then it is purely axial flow machines, purely axial flow machines or axial flow palm. That is why I have drawn this radial and axial direction, and when alpha is equal to 90 degree, then this is purely radial flow machine, purely radial flow machines or radial flow palm. So, alpha depending upon the magnitude of alpha, if alpha typically varies from 15 to 30 degree for mixed flow palm, it becomes 0. When it becomes 0, then it is purely axial flow machines, and when it becomes 90 degree, it is purely radial flow machines. Now, as I said you that in case of a mixed flow palm, there are two components. So, there are two components of flow, one is in the radial direction, another is in the axial directions, and that is why it is called mixed flow palm, and it is used in condenser and cooling water duties. It is used, this mixed flow pump, it is used in condenser for cooling water duties pump. The specific feature of this pump is, specific feature of this pump is, it diameter of the impeller, diameter of the impeller roughly 1.5 meter, is big pump, and power consumption is of the order of 4 megawatt. So, it is used in condenser cooling water duties pump. It has two components of flow, one is in the radial direction, another is in the axial direction, that is why we call it axial flow pump. We have drawn a schematic of the blades impeller, blades hub. So, this alpha typically varies from 15 to 30 degree for the mixed flow pump. The specific feature of this pump is, rather specific features of this pump are, diameter of the impeller is 1.5 meter and power consumption is 4 megawatt. Okay. So, this is all about the classification of rotodynamic pump, and positive displacement pump, as I said that again this is a machine in which there is a physical displacement of the boundary of certain amount of fluid mass as a closed system. So, that is why the name positive displacement comes. Now, we will briefly discuss about the velocity triangles of a radial flow pump. So, if I draw impeller, that is hub as well as blade of a and suppose pump is, impeller is rotating in the clockwise direction. So, this is an impeller of a radial flow pump, this is an impeller of a radial flow pump. We will discuss velocity triangles for all the pumps, axial flow pump as well as the mixed flow pumps. So, before I go to discuss about the Euler's equation of turbo machines, that is which gives us an idea about the head generated by the pump, Euler equation of pump turbines. So, now I will briefly discuss about the velocity triangles. So, this is an impeller of a radial flow pump. As I said that here the direction of fluid is in the radial, is radially outward, that is perpendicular to the axis of the machines. Now, there are two, if I take out a particular blade, these are blades and small one is a hub. So, hub plus blade is the impeller and the impeller is rotating in the clockwise direction. So, if I take out a particular blade and if I draw a zoomed in view of that particular blade, so let us say this is 1 and this is 2. So, 1 is the inlet and 2 is the outlet. So, suffixes 1 and 2 are used to denote inlet and outlet of the pump. So, 1 is the inlet and 2 is the outlet of the pump, and this is the blade and this is rotating in the clockwise direction. So, there are 3 components of velocity, I mean at the inlet and outlet. So, if I draw the velocity tangent at the inlet, so the velocity tangent at the inlet, so this is 1. So, this is the inlet. If I draw the velocity tangle at the inlet, so this is the velocity component C1, I am talking C1, this is the velocity component, I am calling it W1, and this is U1, where C is the absolute velocity of water, W is the velocity of water relative to the blade, velocity relative to the blade or vane, and U is the tangential velocity. So, there are 3 different components of velocity. One is absolute velocity of water C, W is the velocity relative to the blade, and U is the tangential velocity. Now, suffixes 1 is used to denote the velocities at the inlet. Similarly, I can draw the velocity angle at the outlet, that is this is U2, this is C2 and this is W2. C2 is the absolute velocity at the outlet, W2 is the relative velocity at the outlet, and U2 is the tangential velocity at the outlet. Now, this U1 is equal to pi d1 n by 60. Similarly, U2, the tangential velocity is pi d2 n by 60, where d1 and d2 are the diameter of the half inner diameter, outer diameter of the impeller, right. So, now there are so many other issues. So, this alpha, the velocity component C1s, which makes an angle alpha with the absolute velocity, sorry, of the tangential velocity alpha 1, this is beta 1, this is beta 2 and this is alpha 2. So, these are the separate different nomenclatures of angles at the inlet and outlet, we will discuss later. So, before I go to discuss about the Euler equation for pumps, Euler equation of pump turbine, Euler equation for pump and turbine, this is a preliminary idea about the velocity angles at the inlet and outlet of a pump. So, we have seen there are 3 components. One is the tangential velocity, that is because of this impeller is rotating at a certain RPM, and at the inlet and outlet of the impeller, the diameter of the hub and diameter of the impeller are different. So, we are having pi d1 n by 60, pi d2 n by 60. Here for a radial flow pump, U1 not equal to U2, but we will see that for a axial flow pump E1 is equal to U2, because this diameter d1 and d2 are the same, and C1 is the absolute velocity. Now, if I take a particular, say if we draw the inlet velocity triangle separately, we will get like this. So, this is U1, this is C1, this is W1, and component of absolute velocity in the tangential direction, this is known as C theta 1, and component of relative velocity in the tangential direction, I call it W theta 1. So, C theta 1, these are very important to discuss when these are very important when I discuss about the Euler equation of turbo pump. So, C theta 1 is the component of absolute velocity in the tangential direction, absolute velocity in the tangential direction. Similarly, W theta 1 is component of relative velocity in the tangential direction. So, we may have C theta 2 and W theta 2 at the outlet. So, the component of absolute velocity in the tangential direction and component of relative velocity in the tangential directions are C theta 1, W theta 1 at the inlet. Similarly, we may get C theta 2 and W theta 2 at the outlet. Now, the C theta 1 is known as swirl velocity. The component of absolute velocity in the tangential direction, it is known as swirl component of velocity. For there might be a case that is known as purely radial inlet, where C theta 1 will be 0, that is no swirl at the inlet. So, this is defined velocity tangles at the inlet and outlet. So, from this inlet velocity tangle, what we can see that the tangential velocity at the inlet is the summation of C theta 1 plus W theta 1, that is component of absolute velocity in the tangential direction plus component of relative velocity in the tangential direction is the tangential velocity at the inlet. Similarly, we can have U2 is equal to C theta 2 plus W theta 2, that is component of absolute velocity in the tangential direction plus component of relative velocity in the tangential direction is the tangential velocity at the outlet. So, this is the inlet and outlet velocity tangles. As I said that when again I am drawing this inlet velocity tangle. So, this is U1, this is C theta 1 and this is W theta 1, this is W1 and this is C1, this is alpha 1 and this is beta 1. Now, C theta 1, as I said you, this is component of absolute velocity, of water in the tangential direction. So, component of absolute velocity in the tangential direction, which is known as swirl velocity, component of swirl. So, this is swirl component or swirl velocity, or it is swirl component. So, component of absolute velocity in the tangential direction is the swirl velocity or swirl component. So, component of absolute velocity in the tangential direction is the swirl velocity or swirl component. Now, if we do not have swirl, so suppose when C theta 1 is 0, that is no swirl at the inlet, that is no swirl at the inlet, that is purely radial inlet, purely radial inlet pump, where C theta 1 is equal to 0, that is no swirl component at the inlet. So, there the velocity tangles looks like this. This is C1, this is W1. Since U1 is fixed, so this is U1, C1 and this is W1. So, this is alpha 1, alpha 1 is equal to 90 degree, that is purely radial inlet, no component of swirl, no swirl velocity. Now, we will see that when we discuss about Euler equation for pumps, then the component of C theta 1 has a big role to play when we talk about head developed by the pump. Now, C theta 1 may be positive or negative, C theta 1 may be positive or it may be negative or it may be 0. So, when it is 0, that is alpha 1 is equal to 90 degree, this is purely radial inlet, no swirl component. Whether C theta is positive or negative, that means there is a swirl. So, C theta 1 will be positive when the rotation of the impeller and fluid in the same direction. When the rotation of the impeller and fluid in the same direction, and C theta 1 will be negative, we will see that our negative component of swirl velocity may be helpful to the net head developed by the pump, but sometimes it may not be possible to have a negative component of swirl velocity, because it may leads to another problem as far as the pump operation is concerned. So, when C theta 1 is positive, that means when rotation of the impeller and fluid in the same direction, then it becomes positive swirl, or sometimes it may have a negative swirl component of velocity when the rotation of the impeller, when rotation of the impeller and fluid in different directions, in different direction. So, today I have just drawn the inlet and outlet velocity triangles. We have discussed about different component of velocities, and we have seen that the C theta 1, that is component of absolute velocity in the tangential direction, may be 0, may be positive, may be negative. 0 C theta, that is no swirl at the inlet, purely radial inlet. Positive C theta 1, that is positive component of swirl velocity when rotation of the impeller or fluid in the same direction, but we may have a negative swirl, that is when rotation of the impeller and the fluid is in the different direction, and a negative C theta component play a big role, I mean when we need to develop a higher head from a pump. So, today we have discussed about, if I summarize, today we have discussed about the classification of fluid machines broadly, without taking a special case of hydraulic machines. We have classified fluid machines in different ways, that based on the principle of operation, there we have defined turbo machines and positive displacement machine, and we have seen that in case of a turbo machines, when the machine absorb power, they are basically pump, when they produces power, they are basically prime mover or turbine. We may define fluid machines in the depending upon the direction of the fluid in the rotating element. It may be a radial flow, it may be axial flow, or it may be a mixed flow when there are two components of flow direction, both in the axial and radial direction. Also, we have seen that the fluid machines can be classified based on the direction of energy transfer. I mean, it may be a pump, compressor or blower, or it may be a turbine. So, and then we have taken a special case, that is the hydraulic machines, which further can be classified into pumps and turbines, hydraulic turbine and pumps. Pumps can be subclassified into two categories, positive displacement pump and the rotodynamic pump. Positive displacement pump, there are so many, I mean screw pump, jet pump, gear pump, reciprocating pump, and positive displacement pump are used where you require a very low amount of discharge and very high head, where we have discussed that rotodynamic pump can be classified into three categories: radial flow, axial flow and mixed flow. Radial flow pump, flow direction or flow of the fluid in the rotating element or in the impeller is in the radial direction, that is in the direction perpendicular to the axis of the machines, and it is used mainly for domestic purposes and in aircraft engine, where we require a low to moderate, moderate to high head and low discharge. Axial flow machines, we have seen that when flow of the fluid in the pump is mainly in the axial direction, and it is used mainly in the coal mines and irrigation purposes, where you require high discharge, low head. And mixed flow pump, we have seen there are two components of flow of the fluid both in the axial and radial direction, and we have seen that the blade makes an angle alpha with the axis of the impeller. Alpha typically varies from 15 to 30 degree for the mixed flow pump, and it has a specific feature, the diameter is very big, 1.5 meter, and diameter of the impeller, and it consumes a huge amount of power. It is used for the condenser for cooling cooling water duties pump. And then we have taken a radial flow pump, we have tried to draw we have drawn the velocity triangles both at the inlet and outlet, because this velocity triangles is very important to have an idea about the head developed by the pump itself. So, we have seen there are three components of velocities both at the inlet and outlet: absolute velocity of water relative to the vane, and there is tangential velocity. Tangential velocity of the impeller at both at the inlet and outlet are not same because diameters are different, and we have identified that we have decomposed the absolute velocity in the tangential direction and radial relative velocity in the tangential direction, and we have seen that the component of absolute velocity in the tangential direction, which is known as swirl velocity or swirl component, it may be a positive, it may be a negative, or it may be a 0. 0 means that is it has no swirl at the inlet, that is purely radial inlet, while positive and negative c theta, that is positive and negative swirl velocity, we can have, because depending upon the rotation of the impeller and fluid. So, whenever impeller and fluid are rotation of the impeller and fluid are in the same direction, then we may have positive c theta 1, or we may have a negative c theta 1 when they are rotating in a different direction. We will see that the negative c theta 1 has play a big role whenever we are talking about net head developed by the pump, but by creating a negative swirl velocity at the inlet, we may develop higher head, but it creates another problem as far as the pump operation is concerned. We will discuss in the next class. Thank you.